Cool. So a little bit of a reminder of what we were looking at on Friday of last week. So we were considering various ways of counting. So new field of mathematics for us, combinatorics, ways that we can kind of smartly figure out sample spaces without actually needing to go through and brute force check every single possibility. The main methodology that we came upon was this idea of taking a complex event that's kind of made up of a bunch of smaller events. For instance, thinking about the number of ways I can pick an outfit as being comprised of making smaller decisions along the way. What am I wearing for a shirt? What am I wearing for my pants? What am I wearing for my shoes? And taking each of the possible outcomes from our smaller events and just multiplying them all together in order to get the total number of possible outcomes for our larger scale event. This is a similar idea. We didn't really talk about it in those exact terms, but it's a fairly good way to think about it. Similar idea for what we did with like the telephone numbers. If I have 10 different options to fill, the outcome of the large event is the final resulting telephone number, and it is comprised of a bunch of smaller events, that being the particular digit that goes first or the particular digit that goes second or third or fourth or blah, 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 blah. We also started taking a look at this idea of the factorial, which came up in a situation that I described as kind of like counting without replacement. So we saw it primarily when we were considering 10-digit telephone numbers that didn't repeat digits. It's a fairly contrived example, but when we go through, when we run that, we have 10 different options for the first digit of our telephone number. One of those digits gets used up, gets assigned to that first location, and then we have 9 different options for the second, and then 8 for the third, all the way down until we are pigeonholed into only one option for the final digit. And so using our multiplication, this was that like 10 times 9 times 8 times 7 times 6 times 5 times 5 times 4 times 3 times 2 times 1, which we said, well, really, we are going to write this as 10 with this exclamation point afterwards, 10 factorial. If you're needing someplace to write it down, the definition on page 1 would be really good. These were also the various examples that we went over from Friday, if you need to go back and fill it in. But we're going to focus today on page 2. We also looked at this in the context of a variety of contexts. One was thinking about like seating arrangements. If I put a person in a seat, then they cannot occupy another seat, and so they are no longer available to be placed anywhere else. We thought about this in terms of rosters for tennis team lineups. If I have 6 different players, 6 different courts, there is a part of the important thing here, there's a fundamental difference between being played first versus being played second versus being played third. And so taking the kind of total number of options for the players to be playing first, one player gets assigned to court 1, moving on down until we get exactly what we see. We're going to take a look at example 1 here, 1A, just to kind of highlight this. In this case, we were told that a movie theater, this is like a small theater, only one kind of movie playing at a time. We're also going to assume it's not going to play the same movie over and over and over again, or even really more than once if it has a larger catalog. They have screening times for 6 movies. And we want to figure out, we're going to start with figuring out the number of ways that we can arrange those screening times from a catalog of 6 movies. So 6 screening times that match the number of movies that we have. If we think of the first slot here as being representative of the earliest screening time, all the way down into the last slot being the latest, how many options for movies do we have to put into our first screening time? We have 6 different options. That movie gets played, we're not going to reuse it. How many options would we then have for our second screening time? 5, and then 4, and 3, and 2, and 1. And you would multiply these all together, but really we're just going to write this as 6 factorial. Again, something that is worth noting, you get a different schedule if you have a different movie first and a different movie last. So for instance, if the first slot and the last slot traded places, you get a different lineup. It does actually fundamentally change the outcome if you mess with the ordering of the movies, which feels like it's been slightly taken for granted. We didn't highlight this all that much, a little bit with the tennis example. Certainly for the phone number example, it makes a lot of sense. If we are thinking about arranging our phone number, if you switch the second and third digit, if they're not matching, you're going to get a different phone number. You're calling a different person, you have a different outcome. Here, you get a different movie lineup. Now, we took this idea and we started trying to make it a little bit more complex. It's nice when we have 6 movies for 6 slots. They all fit really, really nicely. But what if we have 10 movies for 6 slots, or 10 players for 6 spots on the team, things like that? I guess the example would be 10 students for 6 desks, which would be a sucky example, but it does kind of get that point across. The first thing that I would like to note is that the number of objects that we are arranging hasn't really changed. Which is to say it still matches the number of movies, right? We had 6 movies to assign to a slot. Now we have 10 movies to assign to a slot. So let's consider this. The first 6 slots are the movies that we'll actually show. And the last 4 slots are the movies that we don't really care about. Or maybe not that we don't really care about, but they're the ones that don't end up making the cut. They don't get shown. All right. How many ways can we pick from our catalog of 10 for our first screening time? We have 10 different options for our first screening time. And then for our second screening time, 9, and then for our third, and then 7, and then 6, and then 5. And so we fill out our screen time. And what we're looking at left is the movies that didn't get selected. If we're thinking about ordering the movies that didn't get selected here, how many could fill this first I wasn't selected spot? We have 4 options for what could go there. How many could fill the third I wasn't selected spot? Or the second would be 3, and then 2, and then 1. Okay. Big question for you all. We said that the order does fundamentally impact the first 6, right? If we play a movie first or play a movie second, you get a different schedule. Does order change our outcome, change our schedule if we start shuffling around the last 4? No, we get the same roster. And so we have to the left-hand side of our line a subsection of our movie assignments where order matters. Right? Being chosen first is different than being chosen last. It plays you at an earlier time. Whereas our last four, we see that order doesn't matter. Now, looking at these last four slots, we assign all of the movies for the day. We're focusing on the last four slots. Let's say we literally have these slots filled and we want to know the number of different ways that we can fill a slot given that we have decided on what the roster is going to be. We actually have kind of already done this. What would I do to figure out the number of ways that I can shuffle around those last four slots? It's 4 factorial. It's 4 times 3 times 2 times 1. There are 4 factorial ways to mess with those last 4 slots. All right. And we're saying it doesn't matter. We're saying that really we can do all that shuffling that we like, and it's not going to impact anything. Those 4 factorial different ways to do that, given a particular assignment, given a particular schedule, aren't going to change anything. And so what is this going to look like mathematically? Well, one way that we could do this is we could just say, oh, it's going to be 10 times 9 times 8 times 7 times 6 times 5. And that would be true. You could be done there. But again, that's not very concise, and we could see that the numbers getting even a little bit larger, that could become very, very painful and tedious to write. And so what have we actually modified? This is actually a modification on something. If we're looking at just the number of ways that we can assign a movie to a slot, where we're not worrying about the whole, does the order here matter, does the order here not matter, how many different outcomes can I get of just movie per slot, movie per slot? So ignore the dividing line to start. Yeah, 10 factorial. We have 10 factorial different ways to put some movie in some slot. Now we want to do something to this 10 factorial to eliminate the last 4 times 3 times 2 times 1. What could I do to cancel that last set of 4 times 3 times 2 times 1 that I have attached to this 10 factorial? So is subtracting going to cancel the multiplication that's going on? No, so we need to divide by the order that doesn't matter. This is a really, I think this is an idea that some people kind of struggle with. Think of this 4 factorial that we are dividing by as the ways that we can shuffle the last 4 spots. And we're saying, well, actually, we don't care about what's happening when we're shuffling the last 4 spots. We don't want to have a change in those last 4 spots. Let us consider that the roster is different. We don't want that to be a different outcome. And so we divide it away. We cancel out those last 4 spots by dividing by this 4 factorial. This literally is 10 times 9 times 8 times 7 times 6 times 5. This is that first set of multiplication that we see condensed into a way that's a little bit more digestible. Yeah, that'd be the answer. Box it and call it a day. What we are looking at here, technically what we were looking at before as well, but what we're looking at here is what is called a permutation. A permutation is essentially, given a population, a way to select a certain number of elements from that population, where it matters a lot the order in which these elements are selected. So there's a fundamental difference between being selected first. There's a fundamental difference between being selected second. But note that there is never a fundamental difference between not being selected first and not being selected second, or not being selected last. So what is a permutation going to look like? Couple of different things that we have to define here. The first thing is going to be what we are going to use for n. N is just the size of the sample space. Once I'm sure. N is what we looked at when we were saying there are 10 different objects being assigned to slots. That in this case, N would be the 10 movies that we were choosing from. N would be 10. R or K, you'll see one or the other. We've seen R and K can be kind of changed out for one another, which is a little bit silly, but that's fine. R is going to be the number we choose to select. Or I guess actually just the number we choose. It's a good way to think about it. And so a permutation of size R from a sample space of n, written as this lowercase n, this capital P, this lowercase r. This is, I had a student in fourth ask a fair question, which is what's going on here? Are these like subscripts? Are they powers? Are we raising something to P? This is just like notation. This is just like the way that we kind of collapse what we are looking at here. In just a second. Yeah. Well, I can zoom out a little bit. All right. So this is just notation, and we're not like exponentiating, but what this translates to, what n permutation r is we take our n factorial, the number of ways that we can line up these n objects, and we divide away the orders that we don't care about. In particular, we are dividing away, we don't want to divide away r orderings because that's like what's being chosen. Ideally, we care about that order. We're going to divide away instead n minus r orderings. Just this n minus r factorial. You can think of this as the number of ways to not be chosen. And importantly, really importantly here, the way you cancel or the way you get rid of ordering in this particular case is through division. Mm-hmm. No, n is just the size of the sample space. So notice that in this case, 10 would be the value of n. Yeah, so there are 10 different objects that we are, in this case, movies, 10 different movies that we are considering, and we want to know how many ways we can show 6 of those movies. So in this case, n would be 10 and r would be 6, and that would give us 10 factorial, the number of ways that we can assign a movie to something, dividing out the 4 factorial for the order of the last 4 that we actually don't care about at all. So we care about the order of the 6. Importantly, thing to note here, very, very important, is that this P tells us that order of R, of the chosen, matters. It is fundamentally different to be put in the first time slot versus the second time slot. All right, let's pause here. Questions on our permutation? What we're talking about here with permutations. Yeah, Zoomer. No, so this is all going to be, it's all going to be natural numbers. Okay, so all going to be natural numbers. Technically, we could think about, this is actually an interesting one. You will see this for something like 0 factorial. All right, so for the most part, we're going to be dealing with natural numbers, but I do want to mention this because it's kind of a cool thought experiment to think about. 0 factorial. I have 0 objects that I am trying to arrange into theoretically 0 slots for those objects, right? How many different ways can I order nothing? It's not one. It's not none. It is in fact one. We can't do any shuffling, but that action of not doing anything is an ordering. And so 0 factorial is actually, it's a little bit weird. It's weird. It's a little bit strange. You have to kind of really get into this idea of like how many different ways can I like shuffle these objects and get an outcome. There is only one way to shuffle nothing, and it is by not shuffling it. It's by not doing anything, but that counts as a shuffling. That would be 1. Similarly, 1 factorial, if we have one object in one spot, how many different ways can we put an object into that spot? There is likewise only one way to fill that spot with an object. You would just put the object in that spot. So both of these are actually equal to 1. But otherwise, we're not dealing with negatives. You can't do a negative factorial, basically. Otherwise, it's all going to be whole numbers. You can't do it with fractions either. 1 factorial is also 1. Mm-hmm. Kind of similar to how like raising something to the power of 0, like multiplying by nothing, leaves you with 1. It's a little bit different than that, the logic, but it's similar to how like raising something to the 0th power is 1. And in particular, it's similar to how 0 to the 0th power is 1, which is a little weird, but functional. Good question. Other questions here? If the 0 factorial thing is confusing, don't worry about it. We're not really, it'll come up like tomorrow for a second and then never again. Maybe not never again, but not for our class. Okay, really, really importantly, something that I really want to highlight. This is so far sorting into like being chosen and not being chosen. Think of it as like we have 2 different buckets to fill. We can put either something in the bucket where you are chosen and then it matters the order in which I'm dropping into the bucket, or I can put you in the bucket where you're not being chosen and it doesn't matter the order in which you are dropped into the bucket. You could have more buckets, and we'll see that with C and D in particular. And an important thing to realize is the reason why we are dividing by 4 factorial is because those are the number of spaces that can be shuffled where that shuffling doesn't affect anything. It's the number of ways that those 4 spots can be rearranged, and we're saying that I don't care about those rearrangements. We want to divide away that shuffling to cancel out the order mattering for everything that isn't being chosen. Okay, let's look at a somewhat simple example, and then I'm going to give you guys some time to think about C and D. For example 1B, we have 32 competitors. We're trying to figure out the number of ways for people to finish in the top 4 spots. And we'll assume no ties, so it's not possible for 4 people to all finish first, or for 2 people to finish the first, 2 people to finish third. Not worrying about that. We're going to assume that there is a distinct breakdown, a clear first place, second place, third place, fourth place. Important thing to note, we wouldn't know what to do if this weren't the case, but I do still want to highlight it because it is very, very important, which is that there is a fundamental difference between finishing first and finishing fourth. That is not necessarily a given in this competition, but certainly the way this reads, it's what this is trying to get you to think, that there is something different about finishing first, finishing second, finishing third, finishing fourth, but that those are the only spots we care about. Not to say that finishing 8th and finishing 30th are the same, but for the purposes of what we are considering for this problem, they are to be treated as the same. We are only caring about the top 4 spots. 5th place might as well be last place. Okay. So first and foremost, have to address the sample size, the number of, in this case, people that we are arranging. How many different spots overall, before thinking about where order matters, before thinking about where we're drawing the line, how many spots overall are there? 32 spots, 1 spot per competitor. So we've got the first 4 spots where we are actually paying pretty close attention to who is finishing first, who is finishing second, so on. And then we have the 28 spots that follow, where the order doesn't really matter. All right. How many different ways can we fill our first spot? 32 different ways. How many different ways can we fill our second? 31, and then 30, and then 29. And yeah, we could be done, we can multiply all those. But again, just kind of trying to highlight this point. How many different ways could someone come in 5th? 28, and then 6th would be like 27, and then 26, and then so on all the way down until we have 1 person who is pigeonholed into finishing last. But we're saying that 5th place to 32nd place are to be treated the same. It's effectively the same outcome. Right? And so what is this going to look like? Well, we say we have 32 spots overall, so 32 factorial ways that a person can finish. Ways that we can get a roster, not ways that 32 ways that a person, that one individual can finish, but 32 different ways to fill out, 32 factorial different ways to fill out the overall results chart. But what am I going to divide out? What orderings do I not care about? 28 of those spots can be interchanged as much as I like. And so dividing out 28 factorial, because I can shuffle everything to the right of that dividing line as much as I like, and nothing is going to change. So again, notice the way I deal with having this interchangeability of positions, right? Where I can swap the person who came in 5th and the person who came in 27th, and the top 4 that I care about stay the same. I can swap the person who came in 16th with the person who came in 17th, and it's not affecting the top 4. That result, that outcome doesn't change. That is what I am dividing out when I'm dividing out the 28 factorial, is the number of shufflings that I don't care about. The number of ways those last 4 slots can, or not the last 4, the last 28 slots can be arranged, and we're saying we don't really care about those. All right, C and D are fundamentally a little bit different. It's just a different style of question. But I highly, highly encourage you, at the very least, I want you to grapple with this a little bit. These are tricky, certainly compared to kind of what we were doing here. Think about the slots that can be shuffled without it mattering, without it changing the final outcome. And what did I do, again, with this 28 factorial to pull those out from the overall total number of possibilities? So thinking for both C and D, but I would start with C, and once you feel good about C, then take a look at D. Thinking about what slots can I shuffle that are not going to kind of have that effect, and then how do I modify that overall sample size to adjust for the fact that I can shuffle some of these slots without changing my outcome. First one's perfect. So C is as perfect. Okay. Yes. D is going to be a little bit trickier, mostly just because. Yeah. So the main problem. So the main problem that we have with, say, dividing out 6 factorial is we're saying that those slots can be shuffled in any way that we want, and we don't care about any of those shufflings. So if we think about those 6 objects, can I swap the 2 U's, and would that be like a significant change? Yes. So the 2 U's can swap, and that's not really changing. I definitely want to divide out the 2 U's being able to be swapped. But could I swap a U with an L? So it's a little bit more fine-tuned. So it's gonna be a little bit more of a fine-tune every time. You're gonna want to think about like blocking. You're gonna want to zoom in and really block.
So will I have like multiple of these then?
Yeah, basically. It's tricky, but yeah. So do we know this? Okay, so six different slots to fill. Okay. I actually, the way that we define these slots, we're going to see. I have a fairly abstract way. I'm going to do it to be able to like do this line drawing. But let's think about this in terms of like shufflings that I don't care about. Let's say we define, we fix those various letters. At the end of the day, how many slots will I have that I can shuffle without it affecting my own? How many slots are going to be filled by something that is indistinguishable from something else? What letter do we see repeated? So E is the only letter that can be shuffled in any way without a change. If I swap an S for a C, that's going to change the ordering. That's going to give me something fundamentally different. If I switch the E to E, it's not going to be. Think about how we are going to adjust for that repetition.
Obviously different, but it's fundamental.
So it's going to be a similar idea, but so it's going to kind of happen all at once, where we're going to have this 8 factorial, which is taking into account, it's basically treating swapping 2 L's as being 2 different outcomes. It's taking swapping 2 U's as being 2 different outcomes and all that. We're going to take that one 8 factorial that sees it all as different, and we're going to say, well, actually swapping these 2, not different. Swapping these 2, also not different. So what you get is 1 numerator and then the denominator. It's not 3 different denominators, but it's like 3 different pieces to it. Yeah. We'll look at how I set it, but you're very much in the direction. Okay, so let's look at what we have here. The way that we do. Oh yeah, are you between these 2? Not sure which one. Okay, so the way I like to think of these slots is rather than thinking about them as the position in the word that has a letter that needs to be filled, I instead like to think about them as representing the letter that I need to give a number to that's going to put it somewhere. For instance, this first slot to me might represent where the S goes. This might represent where the L goes. This where the C goes. This where the T goes. And I like these last two both represent. Just because that kind of translates a little bit simpler for me. And so thinking about at which point will I cut off because that swapping is actually going to yield a result. Yeah, so basically it was not like it can be like a nonsense rearrangement. Like you could have.
Does it have to make sense?
No. It can be just like any kind of shuffling. How many different ways can you shuffle these letters and get something that is different than what you had before? Yes. That was, we set some conditions, we set some parameters on our coin toss. So that was like I think we said that the first one was either going to come up a 1 and a 4, a 1 or a 4, and the second one was going to be like even or something like that. So I set some artificial parameters on what that could look like. So how many like total letters do we have overall? So you have the right idea where we want to divide it out, but actually dividing it out is what's going to reduce that sampling space. You still want to start at 6. And think of it as like, the way I like to think about it is rather than thinking about like having a slot to fill in a word, think about it as a position in the word that I'm assigning a letter to. So I have 6 different positions that I could assign the S to. And then after I assign the S, I have like 5 different positions that I could assign the next letter to. Yes, exactly. So the E's, we would not be able to recognize if they were to swap. And so the order in which we see the E's is going to be what doesn't matter. So think about it. So start by the overall like total that we're going to start with is always just going to be, we don't want to think about order. We don't want to think about anything. It's just like, if I'm looking at, we'll assume that they're all the same. So where there is a U1 and U2, we're swapping them is seen as fundamentally different. When we do that, how many different ways could we fill in? 6 with the next one, right? 6 actually. And then we want to divide out the repetition that we see. How many of those ways can we, or how many of those spaces can we shuffle without it affecting? Okay, so let's take a look at C here. I think we're off to some good starts. The way that I am actually going to define my slots is different than how we kind of have in the past. Rather than thinking about my 6-letter word and thinking about ascribing, say, the first letter being an L and the second letter being a C or something along those lines, what I think makes this problem a little bit visually cleaner is to instead think about the letters themselves and for the assignment to be their position in the word that I'm going to give them. So for instance, and you can do this in any order. The order that I'm doing this in is going to be fairly deliberate, just so that we can kind of get a sense for why this is going to be the case. But ultimately, it wouldn't really matter, the order in which you're going to do it, and we'll talk about why here in a second. So for instance, this first slot of mine is going to be where I send my S. The second slot will be what I do with my L. The third slot will be what I do with my C. The fourth slot, what I do with my T. And the last two slots will be what I do with my E. Again, you can do this in any order. I am trying to do this in a way that makes it very, very visually clear what we are doing. But just like how when we were looking at the phone number, I said, well, we could start by assigning the first digit of the phone number. That's fine. It wasn't the only way. We could also start in the middle of the phone number or things like that. So the order in which we have this arranged actually, as far as like assigning to the first slot first, doesn't really matter. The order that matters is the final arrangement of the letters, right? There's something fundamentally different about assigning S to the first slot versus S to the sixth slot. But if I assign S to the first slot after I assign C to the second slot, or vice versa, that doesn't change my outcome. It doesn't actually affect anything. So I can do this in any order that I want. How many different positions in my final word, quote unquote, do I have for if I'm going to put S in there first? How many different locations could S live? 6 different locations. Okay. How many different locations after I have assigned S will I have for L? 5. How many for C? 4 for C, and then for T, 3, and then for E. First E we have 2, and then second E we have 1. But again, I could have assigned the T first. I could have assigned the E first. I'm doing this very deliberately though, so that we can kind of see what happens when what we are left with is kind of what's being pigeonholed here. Okay, so overall, how many different, if we're assuming that each one is completely unique, completely distinct, how many orderings do we have total? 6 factorial orderings, very good. So this would be the number that we get where we can tell the E's apart, basically. But ultimately, for our word, can we tell the E's apart? No. And so if we're thinking about our word, and we've assigned every other position, we've assigned everything other than the E's. The E's are the only 2 left. Does it matter which E comes first and which E comes second? No, it does not matter. How many ways can I arrange those 2 E's such that one comes first and one comes last? 2, or 2 factorial. And so we divide out that 2 factorial to represent the number of arrangements, or maybe the orderings of the E. You can if you want to. I'm also fine with you leaving it as 6 factorial over 2 factorial. Don't say that that's 3. It's not 3. It's definitely not 3. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1. So this number is 6 times 5 times 4 times 3. The exclamation points don't cancel each other. You're not crossing those out. That's like saying ln of 5 divided by ln of 2 is equal to 5 over 2. It's not. Promise you. It's not. LNs don't cancel. Factorials don't cancel. You'd have to write this out as a product in order to do any kind of cancellation. And you can do that, and that's totally fine. Okay. But the important thing that I really want us to understand, the reason why we are dividing out the 2 factorial here is because 2 factorial is the number of ways that I can shuffle some letters and end with the same output. In this case, the only letter that I am able to shuffle is E. If I tried switching S with any of the other letters here, I'm going to get a different output. If I tried switching the T with any of the letters here, I would get a different output, but I can shuffle the E's, and that's okay. I'm not going to change anything. And importantly, there are two different ways to set up two different E's kind of in this word. I can either have my first E come first, or the first E could come second. And those are the only two ways that I can arrange it. So we divide our total sample space by 2 factorial, which is the same as 2. If it was 3 E's, if it was select instead of select, what would I do to my, in that case, 7 factorial? Divided by 3 factorial. In that case, we would have 3 E's that could all be shuffled. How many ways can I take 3 spaces and shuffle them? Well, that would be, I have 3 options for what could go in the first position, 2 options for what could go in the middle position, and then 1 option for what could go in the last position. That would be 3 factorial ways to shuffle the various E's. And we're saying, well, really, we don't want those shufflings to add anything new. And so what do we do to get rid of them? We divide them out. Let's take that logic and see what we can do with D, which is difficult. D is a hard one. I picked one that is deliberately tricky. We could try to do a similar setup here, where maybe the first slot represents where we're going to put A, and the second slot represents where we're going to put S, and the next 2 slots are maybe what we do with the C's, and maybe the next 2 slots are what we do with the L's, and maybe the last 2 slots are what we do with the U's. Something like this. And what I've seen, and this is tempting, to be fair, this is very tempting, is that people drew the line right here. And they said, oh, I have 8 factorial spots to fill. I have 2 that are unique. I have 6 that have repetition. And so I'm just going to divide out 6 factorial orderings. And there's a problem with this. There's a big problem with this. And that is that when we divide out these 6 factorial, what we are claiming is that everything to the right of the line can be shuffled in any way that we want, and it's not going to give us a new outcome, which is sometimes true. For instance, if I shuffle a U and a U, that's not going to give me a new outcome. But it's not always true, because I could shuffle a C and a U, and that would give me a new outcome. So I can't think of everything that has some kind of repetition as being a part of this giant group of things for which order doesn't matter. It's still important how the C's and the L's and the U's relate to one another. So rather than thinking of this as some kind of one lump shuffling, one giant group at the end that we're going to be shuffling, let's instead think of this as smaller groups. Rather, let's think of what we can do with our C's, what we can do with our L's, and what we can do with our U's. So just like before, if I'm not caring about ordering, I'm not worrying about modifying what I have just yet, how many different ways can I fill these spaces? Eight. It's just 8. 8. 8 what? 8 factorial different ways? And if all the letters were unique, we'd be done. But we have some overlap that we have to deal with. So let's make this a smaller problem. Let's first look at what's going on with the C's and think about the number of shufflings that the repeated C's are going to give us that we need to divide out from this 8 factorial. So how many ways can I arrange or shuffle my 2 C's to where we're not going to get something different, basically? 2 different ways. Now, technically, it's like 2 factorial different ways, right? I could either have that first C come in front, or it could come behind the second C. And then the second C is kind of pigeonholed into the other spot. And so there are 2 factorial orderings that are because of the C's that I need to divide out. So thinking we're dividing this out because these are the orderings for the C's. Is that the only repetitive ordering that I see in this problem? No. Where else do I see repetitive ordering? What should I look at next? Yeah, let's look at the L's next. How many different ways can I shuffle the L's and have the same outcomes? Also 2. I could either have the first L here come in front or go behind the second L. And the second L is, again, pigeonholed into being the other option. So I have 2 different ways to organize the L's, which again, this is ordering for the L's. And then one last one for our U's. How many different ways? I again have 2, which I'm going to continue writing as 2 factorial. 2 factorial and 2, again, the exact same thing. But this 2 factorial here, we need to divide out to account for the ordering for the U's. So it's really, really important that we don't think of this as like one lump sum. Like I don't want to divide out by 6 factorial. That dividing out by 6 factorial implies that I could swap the C and the L and that would give me the same output. But I can't. Right, I need to instead focus on, okay, how many non-unique combinations do I get? Well, I get 2 repeated kind of outcomes from whether the first L is in front or whether the second L is in front. I get 2 from whether the first C is in front or whether the second C is in front. And I get 2 from whether the first U is in front or the second U is in front. I need to divide out by 2 3 times, basically, or 2 factorial 3 times. Questions here? Yeah, Dylan. Yeah. Of E. Yeah. It's like the number of ways that we can shuffle E. There are only 2 ways. It's either the first E is in front or the second E is in front. And so we have to divide out those 2 options because they are the same result. They are the same end result. This is all to highlight one really, really, really important idea that we already talked about, but I want to mention again because it's very, very important. And that is that we can undo ordering. We can make ordering not matter by dividing it out. So in this case, I have 2 factorial options for E, or I have 2 factorial orderings for my 2 C's, or 2 factorial orderings for my 2 L's or my 2 U's. And dividing those out from my overall is what ultimately I use in order to not care about those orderings. All right. Let's take a look then. We'll come back to the definition here in a moment. And we're going to, for the moment, ignore what the question is asking us to do. This is more conceptual. I want to see if we can figure this out ourselves. For 2A, we are going to focus on the part that asks us to number all of the possible ways that we can poll 1,000 people from a population of 100,000. Okay. There is something fundamentally different about what we are being asked to do with 2A than anything that we have been asked to do with example 1. Can anyone spot the difference here? What is fundamentally different about this particular setup that we didn't see in the original setup?
You're not dividing on
So we'll assume, it might be fair to say, we'll assume that if we pull one person, we're not going to pull them again. But does it matter the order in which we are pulling people? No. So there is something that we are definitely going to have to adjust for here, which is that the order in which we select people no longer matters. Okay. That should be a fairly actually easy adjustment to make with what we were looking at with the previous couple examples. So first of all, if we're thinking about all of that we have to fill, how many ways can I assign these people? How many different kind of full slots am I trying to fill overall here? What's my value of n? So 1,000 is the ones that I am choosing from my larger subheading. So 100,000 is going to be, think of these as the number of slots that I have to fill. And so the number of ways that I can fill 100,000 slots is 100,000 factorial, some obscenely large number. In terms of like growth, factorial grows slightly slower than x to the power of x. It grows faster than exponential, but it grows slower than if the base is increasing at the same time as the exponent is increasing, which is kind of fun. Okay, so we have our 100,000 slots. Do we care about the order in which people don't get pulled? Does it matter if we say, I'm not going to call Susan, and then after I don't call Susan, I'm not going to call Timothy, and then after we don't call Timothy, I'm not going to call Frank? Does that matter the order in which we are choosing not to call people? Realistically, we shouldn't be choosing at all. If this is a good poll, we're doing this randomly. But it doesn't matter the order in which we don't select. How many people are ultimately going to be put into that not being selected bucket or not being selected category? 99,000? Which is 100,000 minus 1,000. Okay, so this is for the not caring about the order of not being chosen. But that's not the only order that we don't care about. What other order don't we care about? We also don't care about the order in which people are called, right? It doesn't matter whether I am first calling Barbara and then calling Rachel and then calling Bob, and then it doesn't matter that order for my poll if we're doing this poll well. You could really just think of all of them kind of being called all at once. That would be fine. How many different ways? Let's assume that we select our people that we will be called. How many ways could they normally be arranged? What is that number going to be? If I have 1,000 people in 1,000 spots, how many different ways can they be arranged? 1,000 factorial, and we are trying to divide out that ordering, dividing our 100,000 factorial, not just by the 99,000 factorial, but by an additional 1,000 factorial to say, I also don't care about the order in which they are chosen. Okay, so permutation is taking a sample from a larger population where the order in which we select the things in the sample matter. It matters whether you're picked first or second or third or fourth or whatever. A combination is going to be very, very similar, where we are taking a sample size, so the same n. In this case, we do a C for combination, and then the R for the size of the group that we are taking. Just like with our permutation, we start with our unmodified, oh, I have this many slots to fill. Just like our permutation, we don't care about the order of those not being chosen. Unlike a permutation, we also don't care about the order of those being chosen. So in addition to dividing by n minus r factorial, we are also going to divide by r factorial. Which is to say this is the number not chosen, and this is the number chosen. And what that does is it eliminates order from the picture. This is choosing without order. Where? Okay, so example 2 has 2 different parts to it. The first is more conceptual. I'm not really asking you to provide an answer here. I'm more just wanting you to kind of grapple with the choice so that you can decide which formula to use. So the first question is the scenario given an example where order matters for what I have chosen, or is it an example where order doesn't matter for what I have chosen? Then it's, okay, fill out the formula, right? Then it's plug in N, plug in R, go ham, have fun. So let's take a look at example 2 here. Looking at 2b, you're asked to figure out the number of possible ways to select a first, second, third, and fourth place spot for a team competition from an overall team of 15 people. I maybe didn't word this super well, but trying to communicate. In this case, does it feel like in this case that order for those being selected matters? It feels like if we're mentioning that there is a difference in spot, that there's something to being selected first versus something being selected second. There are, I have now since thought of ways that I could have done this a little bit more elegantly, but this is fine. There is a fundamental difference in the order in which we are being selected. All right. If that is the case, is this an example of a permutation or combination? Permutation. And so permutation, I am going to divide out the order of those who were not selected, but I'm going to leave behind the order of those who are selected. So how many spaces are we working with overall? How many options, how many buckets do I have to fill? Well, the buckets analogy is actually that's a bad question, but what's n? What am I working with here? 15 different people to either choose or not choose, and if I'm choosing them, to assign the order in which they go. So I have 15 factorial total possible ways to line these people up. And how many of those slots don't care about order? 11 of the slots don't care about order because only the top 4 care about order. In this case, you could either write this as 15 minus 4 in parentheses factorial, but we can also just say that there are 11 spots that you could shuffle them in any way you like, and it's not going to change the outcome. And so we divide out that 11 factorial. This is equivalent to 15 times 14 times 13 times 12. Okay, for C, we're trying to take a class of 20, trying to pick 3 representatives for our class of 20, from our class of 20. Is this a scenario in which order matters or doesn't matter for those being selected? Doesn't matter. Now, we could imagine a scenario in which it does. Maybe rather than saying just 3 generic representatives, I say that we are picking a president, a vice president, and a treasurer, something like that. Now, all of a sudden, being picked first or being picked into the president role is fundamentally different than being put into the vice president role, is fundamentally different than being put into the treasurer role. But in this case, 3 generic representatives, order doesn't matter. Overall, how many objects, in this case people, are being assigned? 20. So 20 factorial total slots to fill. How much order do we not care about because these people just aren't being chosen at all? 17 slots are just not being picked, so we don't care about the order that they come in. And then how many slots do we not care about the order because being picked for one representative spot is the same as being picked for another? 3 slots that we also don't care about in terms of how we shuffle them, dividing out 17 factorial and 3 factorial. One final one. I could have made this a lot easier. I don't know why I, had to jump through all these hoops. Even numbers between 1 and 31. We want to figure out the number of ways that we can multiply 5 distinct numbers that fit that bill. So that fit between 1 and 31. So, interesting question, or the first question here, does order matter for the order of being selected as part of this product? Why not? Because multiplication is commutative. Very good with that property. Very, very nice. Multiplication is commutative. A times B is the same as B times A. The other word for that is that multiplication under the kind of group that we are working with is abelian. So that's just another way to say that it's commutative. But yeah, exactly. We have this commutative property. We can multiply things in any order we like. It doesn't matter. This multiplication is going to be some kind of combination because it doesn't matter if we pick 2 first and then pick 4, or pick 4 first and then pick 2. We get the same result. How many different numbers are there, even numbers are there between 1 and 31? 15. So we have 15 factorial total different slots of being assigned or not being assigned. How many orderings do we not care about on account of the number not being picked? How many numbers of this 15 are not going to get picked? 10 of the 15 are not going to get picked. And so we don't care about that ordering. And then how many of these numbers do we not care about the ordering for because they are picked, but multiplication is commutative? 5 of those numbers, the order doesn't matter because of commutativity. And so we get this 15 over 10 factorial, 5 factorial. All right, questions here with our permutations combinations. All right, we will call it there. We're going to be looking at how we can kind of tie a lot of this into a very different realm of math. So this whole like counting process shows up in a couple of very surprising places. We're going to be looking at one of those tomorrow, but that'll be the end. That'll be the end of new pre-cal things. And then we've got exam review and then exam for you guys on Thursday. Yeah, Gabby. There will be a quiz on this probably on Monday, but we're going to be done with like learning stuff for the quiz by tomorrow. Yeah. The last quiz will be